Good morning or good afternoon, depending on where you're calling from. My name is Charla, and I want to welcome you to today's webinar, Understanding In-Memory Technologies and Caching Strategies. Before we begin, we do have a couple housekeeping items to go over. Everyone will be muted for the webinar, so please type any questions you may have as we go along into the Q&A panel, and we'll answer as many as we can at the end of the presentation. Also, this webinar session is being recorded and will be sent to everyone via email following the webinar. Now that we've taken care of that, I want to thank you all again for joining today's webinar, Understanding In-Memory Technologies and Caching Strategies, presented by John Desjardins and Manny David. John is the Community Advocate and CTO for North America at Hazelcast, where he's championing the growth of our developer and customer community. His expertise in large-scale computing spans data grids, microservices, cloud, big data, Internet of Things, and machine learning. He's an active blogger and speaker, and he brings over 20 years of experience in architecting and implementing global-scale computing solutions. He'll be joined today by Manny David. Manny is a senior solution architect at Hazelcast with over 24 years of experience in design, development, and implementation of multi-tiered distributed application systems. Manny has played key roles in the development and deployment of large-scale mission-critical e-commerce, healthcare, and financial systems utilizing IMDG technology. And with that, I'm going to go ahead and pass it off to you, John, to start us off.
Thank you. Excited to be here today to talk to everyone. So I'll just be introducing some of the basic reasons why people are interested in caching and in-memory data grids. And then we'll hand that off to Manny to kind of get into more details on strategies. So some of the top pain points that are the reasons why you want to start thinking about this type of technology are, number one is just basically slow applications, slow sites, any kind of a application that's just not responding very quickly, loading data and providing the data to clients. The next one would be overloading and crashing web services. So many microservices or web services are often, trying to retrieve too much data, trying to overcome a lot of challenges with scale, and to do this in a reliable way. And so caching, if it's not done properly, can lead to problems with crashing applications, and at the end of the day, what it creates is a bad experience and slow applications facing your customers. In addition, many times applications are relying on mainframe or other back-end systems that are very costly and expensive to scale. And so trying to move some of that data off of those systems and provide it in memory can make it a lot easier to scale your web applications without driving a lot of cost on the mainframe. And, there's also many applications which just get to a point where more servers isn't actually making anything faster or more available. So when adding hardware with no effect, caching can be one of the things you need to look at. And finally, a lot of times when you get new projects going, you kind of get them up and running very quickly. You're trying to be agile, and then you start to realize that the projects are responding slow. They're not hitting certain SLAs. So at that point, caching can be a quick way to improve performance. Now, data grids are used very extensively. So many of you may be new to these ideas of distributed caching and data grids, but it's used across all major industries, by hundreds of companies. And what we're going to talk to you about today is what are some of the basic use cases and problems that can be solved with caching. So we're primarily talking about the first use case here of being able to have a very fast, high density, highly available cache that's distributed. And at the end of the day, that's provided typically by an in-memory data grid, but an in-memory data grid often offers quite a bit more in terms of capabilities. And so with Hazelcast, there's a lot more that you can do with it than just distributed caching. But we won't get into too much of that today. Microservices are, of course, another key thing, because as we move towards a microservices architecture, we need to be able to scale services more independently. And at the same time, we want to be able to have the same information shared, the same data, the same experience as you're connecting from one node to another, from one microservice to the next. So being able to have distributed caching makes it easier for you to implement microservices architectures. And then, of course, just scaling any web application requires the session and basic user information to be scaled, and the caching technologies are very effective for providing greater scalability of web application sessions. So what are key capabilities of any best-of-breed platform like Hazelcast? The ability to scale out in order to increase capacity, to add nodes, or even sometimes decrease capacity during slow times if you're running on hardware that you want to free up for other things, or if you're running in the cloud and you want to decrease cloud consumption. So that scale up, scale down is a very key capability. Of course, resilience, automatic recovery from failures without losing data, and minimizing the performance impact. That's a very key capability in these types of solutions. And then, you want something that's got a simple programming model, and then at the end of the day, caching is about performance, and therefore your caching application or platform should be very, very highly performant. So I just wanted to kind of introduce you to these basic concepts of why people are doing this and what are some key things to think about. And with that, I'm going to go ahead and turn it over to Manny. Sorry, I did have one use case to illustrate this point, and that is a Visa payments processing. So many payments processors are synchronizing lots of customer data and providing that data to applications that can do time compute in order to do fraud checks, balance checks, credit checks, and all the authorization logic needed in order to process card transactions in real time at extreme scale. And so Visa, has achieved this through using this kind of distributed caching technology. So I'll go ahead and hand it over now to Matt.
Great. Hello, everyone. For the remainder of this webinar, we'll be discussing the strategies and solutions that John alluded to. More specifically, we'll be discussing the what, where, when, and how. So first off, what is a cache? It's a temporary storage. It's not by all means permanent. So there are implementations which make it persistent, but we'll be focusing on the transient nature of cache. Data sets take a long time to calculate or process or originate from another underlying persistent backend. We want to be able to cache these or access them after the first operation. A cache hit occurs whenever data is already available in the cache and can be returned without any additional operation. Caches can have multiple levels. Frequently used are memory. That's the fastest available with our current technologies. Next is SSD. And lastly is slow spinning disk, which really that's what databases are connecting to these days at the bare minimum. What do we cache? We cache HTTP sessions and fragments. What are those? They're really parts of web pages. They're HTML fragments. We want to reduce network traffic and offer the user an instant experience for multiple visits. That's a uh, that's a loaded word. You know, instant experience. So that's quote unquote instant, near real time. A cached object is either calculated or originates from a backend system used in front of the database to reduce queries, and therefore load on the underlying system. The resulting objects are actually can be objects as mapped by ORM tools, specifically object relational mapping tools, or just unmarshaled results of XML and JSON. These caches will act as a proxy between some external resource like a database or web service and your apps server. Now we'll discuss the strategies. The most common one really is distributed or caching, cooperative caching. It's a common way for caching in big systems where you have large amounts of data that need to be cached. Implementations can be as simple as routing requests to all nodes or routes these requests based on some consistent hashing of the requested key. This key can be as simple as a hash code calculation, or it can be a more complex derivation as long as it's consistent. And we want consistency because if you were to put an object in cache and your hash code value changes, you'll never be able to find that object again on the second try or third, etc. Second caching strategy is partial caching. So we don't store all the data inside the cache. We only store portions of that data. So it could be that parts of a page are static and only change if some manual batch job on the back end is running and actually updates, let's say, like a city or zip code or something, and your static page will change at that point. So the partial caching really is based on some existing static data. We will run, again, some kind of rule engine or some kind of even simple business logic to recalculate your static page and serve that page back to your user interface. The third strategy is geographical caching. So you'll have geographical caches located strategically chosen so that their locations are optimized for low latency on request. The regional caches can normally be smaller than the central cache. Because certain caches will handle specific regions with different languages, your data set does not have to represent the full population of your application data. It's often used with partial caching to generate web pages for your static pages, static web pages that we discussed earlier. And actually, there's parts of the static page which actually are dynamic, so we'll be replacing that on the fly with the cache data. Then we have the preemptive caching. So this is also used in conjunction with the previous strategies. The idea behind this is to reload data from any backend service or central cluster even before a requester wants to retrieve the element. This keeps access time to the cached elements constant and prevents accesses to single elements from becoming unexpectedly too long. However, building a preemptive cache is probably one of the more complicated tasks. You need a good amount of domain knowledge and workflows to implement this type of caching strategy. Then the last strategy is latency SLA. So you're trying to maintain some type of service level agreement with your users. Let's say you want like a 5-second response time. So here you're trying to, you have two options in implementing this. You can either implement a short timeout. So if your read to the cache is taking too long, you're going to read to the back end. Your second option is to fire parallel reads and take your first response. This option is suitable for cases where you have multiple clusters available to you. Let's move on to topologies. So in-process cache is actually a non-distributed implementation of cache. It's kept inside the application's memory space. Most applications or projects actually start out with in-process cache. So if you think about let's say a Java application using a hash map, for instance, or a concurrency map, that is a Java feature which is not distributed. The type of cache is used for caching database entities, but can also be used as some kind of object pool or instance pooling. So this tries to solve the problem of too much network traffic, as any cache solution would. So advantages are high access speed because your data is available locally, and it's easy to maintain because the code is located with your application. The disadvantages are data duplication. So if you have multiple instances of your application running, you're actually duplicating that data inside of each of your applications. So you have a problem with high memory consumption on a single node or your multiple nodes. And the challenges are really related to memory management and CPU load on your system. Another topology is embedded node cache. This is actually a combination of in-process and distributed caching. It can either use partitioning or full data set replication. When we say partitioning, we're talking about sharding of data, and full data set means just like in a RAID 1 or RAID 0 scenario, you're actually creating copies of your data in each and every one of your application JVMs. By using data partitioning, though, the application knows about the owner of a requested record that may not necessarily reside in the memory space of that application. And that's where sharding gets you the distributed nature of caching. The most common deployment is actually client-server cache. This tends to be a multi-server architecture, which is easy to scale out and has the same features as the embedded node caches, but your application is actually separate from the cache layer. This gives you allows you the simplicity of actually scaling the application cluster or actually caching your or scaling out your caching cluster independently. It's quite similar to the common usage patterns of an external relational database or network concerned backend resources. So this is your typical multi-tier architecture, which a lot of enterprise developers are used to. Keep in mind, though, the disadvantages I pointed out there. The last one is always an additional network round trip. So when you're distributing data, your data is at least one network hop away from you. So that's a round trip. So we currently, with our technology, we don't have a infinite amount of memory, but the cost of memory keeps decreasing as we move forward here. So eventually, we may have a notion of infinite, but we're not there yet. So we have to deal with the bounded RAM, or random access memory. So let's talk about eviction strategies. So eventually you will run out of memory. So we need to control that, right? So the first strategy is least frequently used. So basically you remove values that are accessed the least amount of times. Each access for each record results in a counter increment, as it shows there in the diagram. Uh, it takes the age of the element into account. It counts reference frequency and works better under a high load. Um, your disadvantages are the frequently accessed element will only be evicted after a lot of misses. So, and depending on your use case, um, this may not give you the synchronization needs that you need with your backend. Then we have the least recently used. So remove the oldest used values that are accessed the least in terms of time. Each access for each record results in an update of the last access timestamp. Um, it's the most optimal algorithm. It's least load on your system. Disadvantages, not as effective since it's more important how often an element was accessed and when it was accessed. A third one I added on there is a time to live. So, given your eviction strategies, we also want to provide a time to live for an entry. So, it gives an entry a duration for its existence, really. Um, the advantages are you get a per entry duration. So, it doesn't matter, each object you store in your cache has its own duration. It forces more frequent invalidation depending on your use case. Um, but you need to ensure that your invalidation occurs at the right duration if your underlying data store is changing as well on its own or being updated by a third party. Now let's talk about the caching solutions. First off, Hazelcast is an in-memory data grid. It's a object-oriented and non-relational store, NoSQL data store. It provides a simple modern API, much like you're used to with the Java APIs. We also provide some distributed data structures out of the box to make distribution simpler. You don't need to concern yourself about data distribution. And also, the grid portion of Hazelcast IMDG is the compute. So we provide a distributed compute feature so that you can take advantage of multiple nodes and multiple processors. We support standard JDK collections such as lists and sets. And the queues are what you're used to with typical message processing like pub sub and queue. From the perspective of a developer or DevOps, clustering is automatically supported. Um, Hazelcast is elastic and scalable. We have a management center, which is a web-based cluster management feature. So you can monitor and manage um, your IMDG cluster. And we provide a transparent database integration via APIs, interfaces that we provide, and then you will need to provide your your drivers, your resources, like a Type 4 driver or file system handler, etc. And from the client perspective, we're a polyglot. So we support Java, .NET, Python, Node.js, and Scala, and that list keeps growing. As we mentioned earlier about strategies and cache types, we have two deployment options, embedded and client server mode. So on the left there, you'll see that Hazelcast IMDG is embedded in the same Java virtual machine as your application. So the data is sitting side by side with your application. It's great for microservices, and because you package, microservices you typically package small, and Hazelcast is by our very design, it's packaged. Actually, you only need one jar file. Like I mentioned earlier, client server mode is the more common deployment. Easy to scale up. And as you can see there on the right side of the diagram, the polyglot support that we provide, and your data cluster is separate from your application. So our typical use case is a web session cluster. So it provides fast session access, offload any operations to your existing cluster, and we support Tomcat, Jetty, and generic web servers. With clustering, you get automatic session failover, and you don't lose your data because typically you'll have multiple nodes running and you have backups configured. This is a typical actual deployment of a web session cluster. So you have a balancer in front of your users, and the load balancer will typically select the web servers on the middle tier layer. So that could, if you knock out one of your app servers, like server 3, for instance, you still have server 1 and 2, and you still have all your session data available to you, even though your user was originally on server 3. A typical use case for a multi-tier application, like we talked about earlier, you have your business systems on top, so that would be your client, and Hazelcast IMDG in the middle, and you have any and many persistent backend storage like RDBMS, even mainframe DB2, NoSQL, MongoDB, REST, whatever you want to do, even file system if you'd like. The more common trajectory for new projects are microservices architectures. Their goal is to reduce restoration time after failure, ease of adding new functionality without affecting users, because your app can come and go, but in a microservice architecture, we always have a server to service a request. It's modular in nature for larger teams, so they could deploy their microservices. Most in large organizations, specific teams are responsible for developing specific microservices. So they are not tied to the entire enterprise. Deployment options for your microservices. So here we have a client server and also embedded on the right side. So the left side, your cluster is actually separated from your microservice container but your microservices container is calling out via various clients to the Hazelcast cluster. On the right side, Hazelcast is embedded with each microservice. If you see there's microservice 1, 2, and 3, and they have their own Hazelcast cache. So that's a common deployment as well. You in this on the right side, you have microservice service isolation if you don't want to mix your data. Other deployment options. This is actually a more another implementation of client server. So what we have here, we have a specific microservice and a client accessing the Hazelcast cluster, and the second one is microservice 2 using Python. So this is another client server architecture, really. Okay, we're at that point.
Perfect, Manny. That was a lot of great information. Wow, I can't believe you got through it all. So we do have a couple questions that are coming in. Our first question is there a strategy available whereby expired entries are not evicted but returned and then updated I can't even say the word, Manny. Asynchronously. So like asynchronously.
So
tough words.
Sorry, reread that.
Is there a strategy available whereby expired entries are not evicted but then returned and updated?
Returned and updated.
Mm-hmm.
So at some point you have to invalidate the entry. You need to trigger some kind of validation in order to do an automatic read from your backend. So I don't think we have that feature. Mm-hmm. We do have feature requests coming up by some of our enterprise customers related to something like read ahead. So let's say you have you provide actually it's a time to read for instead of a time to live. So let's say you want to reread from your database every 5 or 10 seconds. So we want to add that feature in Hazelcast, but that's not in there yet.
Great. Our next question says you call it a grid. Could you explain what you mean by a grid?
So a grid really, when we're talking about grids, I'm talking about compute grid. So this is, if you think about an infrastructure where you have multiple virtual machines running to share your underlying physical hardware. So when I say grid, I'm talking about each of those virtual machines working in harmony with each other and synchronizing with each other and performing certain tasks that are handed to them in unison.
Perfect, thank you. Which caching strategies are best for improving availability of microservices?
Which one are they saying? So yeah, depending on the size of your data that you want to cache, you can either use embedded or client server methodology. If the size of your data is too large for a individual node, you might have to go client server, in which your microservice is actually a client of your INDG cluster. Reason being is if you have many nodes that are starting and stopping, Hazelcast actually keeps track of who's coming and who's going. And if a node leaves a cluster, it actually triggers a migration event, in which case the whole system is put on notice saying, hey, I am going to start moving data around, and I'm going to restrict you from writing any data. But what I will do is allow you to execute read operations.
Perfect. And then, so our next question is geographic caching a good use case for addressing performance for content-intensive applications?
Absolutely. Sorry.
Hold on, folks. We're just having a little bit of technical difficulties. There we go.
Yeah.
Alrighty, so the question is, geographic
caching.
caching, a good use for addressing performance
Yeah.
for content-intensive applications.
Absolutely. As I mentioned earlier, the slide actually had basically we were partially caching as well, and static HTML pages had some dynamic components to them, and we talked about reducing latency for the loading of pictures and MP4s, for instance, right? You want to cache that. You want to have that as close to the user as possible. So we almost always know the location of the user, so we can actually try to the load balancer can try to figure out the closest Hazelcast cluster, and we could also share data across multiple geographic locations. So whatever you do in one geographic location, your data can be eventually propagated to your central cluster.
Perfect. Our next question, and forgive me if I mispronounce anything, I am not a technical person here. By using JRE heap for caching, does it not affect garbage collection activity adversely?
Absolutely. So your Java garbage collector is greatly affected by the fact that you are storing, keeping references to many objects. So eventually, the garbage collector will need to decide whether these objects need to be whether the garbage collector needs to perform a full garbage collection, in which case a stop the world GC occurs, in which I think a lot of many developers and ops people know is not a very good thing. So your if you are not using the enterprise version, which actually bypasses the Java garbage collector, your application needs to be tuned such that you will handle, you're optimized for minor GCs and also full GCs if and when they should occur. So, like I said, if you were to use the enterprise feature, which is the high density memory store feature, we actually have our own garbage collector, which will bypass any default Java garbage collector and is optimized so that there is no stop the world GC occurring in your application.
Thank you, Manny. So we're getting quite a few questions still coming in. Why would an IMDG require a database integration? What are the scenarios where you would use it?
Good question. So let's say you have, if your IMDG or your enterprise project is not the system of record, then I would imagine you would have a persistent storage out there, and typically that would be the case for a legacy system that's undergoing some type of transformation. So yes, you will have you can have many connections to your database, and one of them being your enterprise application that you're working on that's writing updates to the database, and other applications that are not a part of your project, they will have to read from the database. So that's when you would need to synchronize with the database. Now, if you are a new project and you have control of your data, in which case you are the system of record, then you do not need a back-end database.
Perfect. We have a question that's referring to, I'm guessing, page 30 of the slides. It says the connectors to various databases like RDBMS, Mongo, etc. Is it really applicable to IMDG? Now to find reference the slide 30.
Oh, almost there. Sorry, folks. Okay. I think I have the picture in mind, but let's bring it up for everyone. 29, right?
That must be it. Yep.
Sorry. What was the question?
It says the connectors to various databases like the RDBMS and Mongo, etc. Is it really applicable to IMDG?
This is actually related to the previous question. So why are you connecting to a backend persistent store? And the reasons I stated are actually why you would connect to an RDBMS, a MongoDB, or even a mainframe, or even a file system. So sometimes you cannot get away from pushing your data to another backend storage until your modernization efforts are complete and you have full control of your data.
Perfect. Yes, so those were all from the same person. So I'm guessing the next one, either you've answered it already, but just to make sure that he gets the answers that he's needing, he's asking for obviously the seeding of the data to IMDG is still the responsibility of the application, correct? And there is no connectors to the external data sources for automatic data sending.
Yes, there are connections, just like the lines indicate there. We do connect to any of your backend storage. Now, you mentioned seeding of data. So that is, you're right. It is up to the application. Although with Hazelcast, you can configure it such that we'll do eager loading for you or lazy loading. So what I mean by that is eager loading will try to load a good amount of your data. So that's the read ahead, the preemptive caching that we talked about. And also the lazy load, which means anytime, the very first time you access a key, it will not be in memory. So we will go to the backend storage for you to load it, and then subsequent calls to that key will no longer require a database lookup.
Perfect. Thank you so much, Manny. That was a lot of questions. I'm sure that some of you might still have questions that you're thinking about. We will reach out after the webinar so that you can get any of those answered. So I want to thank both John and Manny for a great presentation and so much information. And thank all of you for taking the time to join us for this webinar, Understanding In-Memory Technologies and Caching Strategies. We'll be sending out an email with the link to the recording, as well as the links to all the resources that were shown in today's webinar. I also posted in the chat channel a couple of our resources that you might find helpful. One is a white paper for Caching Strategies Explained. Another is our Hazelcast IMDG Deployment and Operations Guide, as well as an architect's view of Hazelcast IMDG. Hopefully that'll help get you some answers. But again, please feel free to reach out to us. You can learn more at www.hazelcast.org. And again, thank you everybody for joining us, and we hope you have a great rest of your day.